Hello, my name is Drew Jamieson. I am a postdoc at the Max Planck Institute for Astrophysics, and in this talk, I'm going to be presenting some compressed estimators for parity violating statistics in cosmology. The motivation for developing these compressed estimators is that inflationary physics could potentially produce parity violating signatures, for example, arising from Chern-Simons couplings of axion-like fields that may have been around during inflation. If that were the case, then these parity violating signatures would imprint themselves onto the CMB and onto the galaxy distribution in the late-time large-scale structure. And so using observations of these things, we can constrain the primordial parity violations and then potentially learn something about the early universe and about inflation. Now, in order to do this, we need to measure at the lowest order the 4-point statistics. And this can be challenging and somewhat slow. And so my collaborators and I have been developing these compressed estimators for parity violating statistics, which evaluate more like power spectra and which are fairly easy to model theoretically. So to begin, we'll ask the general question of, well, how do you construct a parity violating power spectrum to begin with? One example is if I have a vector field, which is parity odd, so it gets a minus sign under parity, and I have a pseudo-vector field, which is parity even, so it does not get a minus sign under parity, then the dot product between these two things is a pseudoscalar. And so if I compute the cross power spectrum between the vector field and the pseudo-vector field, I get some parity odd power spectrum. So this is my parity violating power spectrum. And this is the construction that we're looking at here. Now, how does this relate to the CMB or large-scale structure observables? These observables, as long as I'm not considering any primordial gravitational wave, they all originate in the primordial potential. So all I have is one scalar field to work with. Constructing a vector field is, of course, easy. I just have to take a gradient of the scalar field. But to get a pseudo-vector field, I need to do something more complicated, something non-trivial. So one example of something I can do is I can define or just choose some kernel, Ka, and I can smooth the potential by multiplying the modes of the potential by this kernel, Ka. Then I get another scalar field, phi a. If I define two different kernels, Ka and Kb, then I can construct this composite field, phi a grad phi b. And as long as the two kernels used to define them are different, then this composite field is a vector field that isn't just the gradient of a scalar. Since it isn't just the gradient of a scalar, I can do a Helmholtz decomposition. So I can define this composite field to be this vector field VAB, which is phi a grad phi b. And I can always decompose this into the gradient of something plus the curl of something else. And the thing that I'm taking the curl of here has to be a pseudo-vector. I can tell that because the vector itself is parity odd, so it gets a minus sign under parity, but the spatial derivative in the curl is already parity odd, so A must be parity even. And so that means it's a pseudo-vector. I can isolate this pseudo-vector by taking the curl of the vector field and then solving a Poisson equation, where I'm imposing that the divergence of this pseudo-vector vanishes. Then, in general, what I can do is define 4 different kernels, K, A, B, C, and D. With A and B, I define this vector field, VAB, and with C and D, I define the vector field, VCD, and then isolate this pseudo-vector from it. Then, once I have these two things, I can calculate their cross power spectrum, and that gives me my parity violating power spectrum. Now, in order to gain maybe a little more insight into what it is that we're doing here with this construction, we can note that the Helmholtz decomposition is incomplete in the sense that I've sort of chosen a basis vector in Fourier space in the longitudinal direction, which is k hat, but I haven't yet specified a basis for the transverse space, which corresponds to the curl term. I can do this by choosing, for example, the right-handed and left-handed polarization vectors. These are the eigenvectors of the curl operator with positive and negative eigenvalue. Now, the parity operation swaps the left-handed and right-handed polarization vectors. And so that means it swaps the right-handed and left-handed modes of the field. Then using that fact, I can actually just construct a parity odd and even basis by taking the sum or the difference between the right-handed and the left-handed polarization vectors. And so I can do this decomposition of this vector field into longitudinal part and a part corresponding to the even polarization vector and a part corresponding to the odd polarization vector. If I do this and I look at the composite field power spectrum that I constructed earlier with a vector and a pseudo-vector, it turns out that this is really proportional to the cross correlation of the parity even and parity odd parts of the vector field. So this is the way in which we've really isolated this kind of parity odd statistic. Of course, in this case, we get the sum of these two terms. We could just do this decomposition and look at the V plus cross V minus, which would also be a parity violating statistic. But here I'm going to focus on the vector cross pseudo-vector construction. Now, in order to make contact with the parity violating trispectrum, which is ultimately where this parity violating signal must come from, we can look at the Dirac delta function that always comes with the trispectrum and imposes translational invariance by requiring that the sum of these wave vectors vanish. So that means that these wave vectors k1, 2, 3, and 4 form a closed loop in Fourier space. So they form a tetrahedron. And I can look at this tetrahedron as two triangles, one formed by k1 and k2, and one formed by k3 and k4, that are glued together along an edge of common length, capital K. Now, if I take a look at my vector pseudo-vector cross power spectrum, it turns out that this is an average, a weighted average over the primordial trispectrum, which here I'll call tau minus, averaging over the vectors k1, k2, k3, and k4, but holding this diagonal side k fixed. And this capital K is what really corresponds to the argument of the power spectrum. So this is the way in which we're compressing the parity violating trispectrum down into a power spectrum. So we can test this construction and test our estimator by setting up random non-Gaussian primordial potentials and then measuring this estimator on these fields and checking to see whether or not they actually give us back what we expect them to. So we set up our primordial potential as some template, which corresponds to a random Gaussian field, phi g, plus some nonlinear transformation of that random Gaussian field. It involves a triple product, which is ultimately where our parity violating statistic comes from, and then two versions of the field that are transformed by having their modes rescaled by the magnitude of the wave vector to some power, and the powers are -1 and -2. This gives us a template for this parity odd primordial trispectrum, which equals this triple product, of course, and then the primordial power spectrum raised to the power 3. Here I'm just setting the spectral tilt ns equals to 1 for simplicity. And then I get a factor, which is a sum of terms, 24 different terms, which are the 24 permutations of the wave vectors, k1, 2, 3, and 4. For odd permutations, I get a minus sign, and for even permutations, I get a plus sign. And each term comes with the fixed set of exponents, -3, -4, -5, and 0. And that is what gives this template its particular shape. So I can impose some ordering on the tetrahedrons, and I can impose some binning scheme for them. And then I can look at what the shape of this primordial trispectrum is as a function from roughly large scales to small scales. And you can see it has this sort of characteristic pattern, repeating pattern of peaks. And the repeating pattern is indicative of the scale invariance of the template that we're setting up here. So now that we have some template that we're setting up and generating random boxes of, we need to make some choices for the compressed estimator. In particular, we need to choose the kernels that we're going to use. So the ones that we chose to look at have one of them proportional to the magnitude of the wave vector squared. Another is the magnitude of the wave vector to the power -2. And then the other two are just simply proportional to the identity. But all four of them involve scale cuts. So we impose a minimum and a maximum wave number magnitude that we're going to look at for all four versions of the field. And then we set up these boxes with a length that we're going to interpret as 1 gigaparsec over h, and a grid size of 512 cubed grid sites per box. And then we generate 64 pairs of these boxes with this primordial potential, where we've injected this parity violating trispectrum. For half of the boxes, we chose a positive sign for the amplitude of the primordial trispectrum, and for the other half, we choose a negative sign. And for both sets of boxes, they both have the same set of underlying random Gaussian fields used to generate them. So you can see here, this is the shape of this vector, pseudo-vector power spectrum that we've constructed. And the white curve corresponds to basically a theoretical calculation where we can analytically do all of the angular integrals involved in this, and then numerically compute the remaining radial integrals for the magnitudes of the wave vectors in Fourier space. And you see we get excellent agreement between our theoretical prediction and the data that we've generated to basically have this particular parity violating signal. Of course, we can take these pairs of boxes, and since they both have the same random Gaussian field, we can subtract the ones with positive amplitude and the ones with negative amplitude to get variance suppression. Then we get a very sort of clean, smooth signal here, which matches well with our theoretical calculation. So this shows that we've generated this primordial parity violating signal, and that our compressed estimator is indeed sensitive to it and able to accurately extract it in a way that we can also theoretically model very accurately. So this is kind of an efficient way of getting this, for example, this amplitude for the parity violating template that we have here. Now we can ask another question, which is this the only thing that we can do? What we've done so far is construct a vector field and a pseudo-vector field, which are both order phi squared. And that means that the cross power spectrum between them is order phi squared cross phi squared. So of course it's order phi to the fourth, because after all, what we need to be doing is compressing down the 4-point statistics, the trispectrum. But what about the possibility of phi to the power 1 cross phi to the power 3? This is also something that should give us a compressed estimator for this parity violating statistics. So what this corresponds to is actually directly constructing a pseudo scalar field from the primordial potential. So again, we have these smoothing kernels, K, A, B, and C, and we construct these different fields, phi A, phi B, and phi C. And then taking their gradients, we can form this triple product, and this gives us some pseudo-scalar field. Then we compute the cross power spectrum between that and the original potential, and that gives us some parity violating power spectrum again. Now, in this case, instead of being the diagonal capital K of this tetrahedron that we have as our argument, the argument of the power spectrum is really one of the side lengths for the 4 wave vectors that form the tetrahedron. In this case, I've relabeled K1 as just K, and K2, K3, and K4, and the diagonal capital K are the things that we're averaging over in order to get our compressed statistic. There's actually more freedom here than I've introduced into this equation. We could, for instance, at an intermediate stage, introduce a smoothing kernel for the diagonal capital K and include that here. But this is a detail that I'm not going to consider here. So once again, we can look at these random boxes that we've generated with this sort of injected primordial trispectrum signal. And we can construct this new estimator for the scalar cross pseudoscalar power spectrum. And again, we can do our theoretical calculation, and we find that it matches the data well. We have our boxes with the positive amplitude for the trispectrum and boxes with the negative amplitude. And then taking the difference between them, we can do this variance suppression, and we get excellent agreement between our theoretical calculation and the data that we've generated in these boxes. So again, this is another option for looking at parity violating statistics in a compressed way that's fast and fairly easy to evaluate, and also fairly easy to model theoretically in the sense that if we know what shape of the trispectrum we're looking for, we can get predictions for what these compressed statistics should look like. Another thing that we can look at is what happens when we consider the linear matter field instead of just the primordial potential. Of course, ultimately, what we're interested in for large-scale structure is the nonlinear matter field, and that is a complicated detail that we will look at in future work. But here we're just going to consider what happens when you take the primordial potential and then rescale it by the transfer functions, and then say a linear growth factor to scale it to some later redshift. In this case, each four products of this primordial potential come with some transfer function that convert it into the linear matter field. And so this is just like changing which smoothing kernels we're using to construct our compressed estimator. So in general, the presence of the transfer functions will change the overall amplitude of the whole signal and change the overall shape numerically. But really, you can see that this is just kind of reweighting the weights in some way that basically preserves the qualitative features of the shape of this power spectrum. So we still see this kind of rising bump here, and then this minimum, and then again, it rises to some maximum. I should say the reason why I'm cutting it off here, even though it looks like the signal's maybe still doing something interesting, is that I filtered the modes so that k of 0.2 is where they're cut off. So actually, the signal is exactly 0 outside of this range. If I smoothed in a different way, then the whole shape of this thing would change. And so we have our vector, pseudo-vector, and our scalar, pseudo-scalar versions of these compressed statistics for primordial parity violations. And we can get very characteristic shapes, which we could then use to go look for these parity violating signals. Now, the outlook is, of course, that there's a lot to do. This is kind of a first step in the process. So we're interested in looking at the real space counterparts of these compressed statistics. We're also interested, of course, in looking at harmonic space and projected along the line of sight statistics, as well as the effects of redshift space distortions. And of course, for the large-scale structure, looking at how nonlinear evolution will affect these kinds of things, as well as the effects of looking at bias tracers such as halos and galaxies. And ultimately, the plan is to adapt these for realistic survey data conditions where you have complicated masks and windows that you also need to take into account. And then so hopefully we'll develop these things and be able to apply this to real data and get efficient constraints of parity violating statistics. Thank you for taking the time and listening to my talk.